For a 200 amp service, the selection of a grounding conductor involves understanding the requirements outlined in the National Electrical Code, specifically Table 250.66, and how these relate to conductors used in service entrance cable or SER cable. Table 250.66 provides the minimum size for grounding electrode conductors based on the size of the service entrance conductors. According to Table 250.66, for 200 amp service, a minimum of a number 4 American wire gauge or AWG bare copper conductor is typically specified as the grounding electrode conductor. This size is determined to safely carry the maximum fault current that the system could experience, ensuring that the grounding path could effectively facilitate the operation of overcurrent protective devices like circuit breakers or fuses in the event of a fault. The code mandates this minimum size to protect against electrical shock and to minimize the risk of fire by providing a low impedance path for fault currents. Now let's consider the use of a number 1 AWG bare copper conductor in a 2/0 copper SER cable. Service entrance cable, including SER cable, is commonly used in residential applications to bring power from the service drop or service lateral to the main service panel. These cables are designed to be durable and suitable for direct burial or installation in conduit, depending on the specific type and local regulations. The inclusion of a number 1 AWG bare copper conductor as the grounding conductor within a 2/0 copper SER cable might seem inconsistent with the minimum size specified in Table 250.66. However, there are several factors that justify this discrepancy. Firstly, the grounding conductor with an SER cable is typically an equipment grounding conductor or EGC rather than a grounding electrode conductor. The equipment grounding conductor's role is to provide a low impedance path for fault current back to the source, thereby facilitating the quick operation of overcurrent protective devices. Secondly, the ampacity and overall design of the SER cable are engineered to meet specific standards, ensuring that all conductors within the cable, including the grounding conductor, are appropriately sized for the intended application. The number 1 AWG conductor is often chosen for its balance of current carrying capacity, flexibility, and ease of installation. Although it is smaller than the minimum size that Table 250.66 might suggest, it's still capable of safely handling the anticipated fault currents within the context of the SER cable's overall design and application. The smaller size of the number 1 AWG conductor compared to a number 4 AWG conductor offers significant advantages in terms of flexibility and ease of handling, particularly in residential settings where space is often limited and installations may require navigating tight bends and corners. The more flexible conductor simplifies the installation process, reducing the risk of damage to the cable and making it easier to work with. The National Electrical Code permits the use of smaller equipment grounding conductors in certain situations, provided that they are sized appropriately for the circuit's overcurrent protection. This allowance recognizes that the actual fault current magnitude and duration are key factors in determining the required size of the grounding conductor. The equipment grounding conductor must be able to safely carry the available fault current long enough for the overcurrent protective device to operate in cleared fault. In many residential applications, the available fault current is relatively low, and a number 1 AWG conductor is sufficient to meet this requirement. When deciding whether to use a number 4 AWG bare copper conductor or a number 1 AWG bare copper conductor in a 2/0 copper SER cable for a 200 amp service, it's important to consider the specific requirements of the installation and the local electrical codes. If using individual conductors in conduit, adhering to Table 250.66 and selecting a minimum of a number 4 AWG bare copper conductor is essential. However, if using a pre-manufactured 2/0 copper SER cable with a number 1 AWG bare copper grounding conductor, this is generally acceptable, as the cable is designed and tested to meet the necessary safety standards. Always consult with a qualified electrician and local electrical inspector to ensure compliance with all applicable codes and regulations. They can provide guidance based on the specific details of the installation and ensure that the grounding system is safe and effective. Here is a more in-depth explanation about sizing the grounding electrode conductor or GEC based on table 250.66 and the equipment grounding conductor or EGC based on table 250.122. Understanding how to appropriately size grounding conductors is critical for ensuring electrical safety and compliance with the National Electrical Code. The NEC specifies different requirements for grounding electrode conductors or GEC and equipment grounding conductors or EGC, each serving a distinct purpose within the electrical system. The grounding electrode conductor or GEC connects the electrical system to the grounding electrode, such as a ground rod, metal water pipe, or ground ring, establishing a reference point for voltage and providing a path for fault current to return to the source. The size of the GEC is determined by table 250.66 of the NEC, which bases the minimum conductor size on the size of the service entrance conductors. To determine the appropriate GEC size, firstly, identify the size of the service entrance conductors. These are the conductors that bring power from the utility company's service drop or lateral to the main service disconnect. Secondly, locate the corresponding GEC size in table 250.66, using the material of the service entrance conductors copper, aluminum, or copper-clad aluminum as a guide. The table provides minimum sizes for GEC based on the size of the service entrance conductors. It's important to note that table 250.66 provides minimum sizes, and larger conductors may be required in certain situations, such as when the grounding electrode system has a high impedance or when local codes require larger conductors. The equipment grounding conductor, or EGC, on the other hand, provides a low impedance path for fault current from electrical equipment back to the source, facilitating the quick operation of overcurrent protective devices and minimizing the risk of electrical shock. The size of the EGC is determined by table 250.122 of the NEC, which bases the minimum conductor size on the rating of the overcurrent protective device protecting the circuit. To determine the appropriate EGC size, firstly, identify the rating of the overcurrent protective device protecting the circuit. This is typically a circuit breaker or fuse. Secondly, locate the corresponding EGC size in table 250.122, using the type of conductor copper or aluminum as a guide. The table provides minimum sizes for EGC based on the rating of the overcurrent protective device. For example, if a 20 amp circuit breaker protects a circuit, table 250.122 specifies a minimum of a number 12 AWG copper conductor as the EGC. Similarly to GEC, table 250.122 provides minimum sizes, and larger conductors may be required in certain situations, such as when the circuit is subject to voltage drop or when the equipment is located in a hazardous location. When installing EGC, it's important to ensure that they are properly connected to the equipment and to the grounding system. EGC can be installed as individual conductors, such as green insulated wires, or as part of a cable assembly, such as armored cable or metal-clad cable. In some cases, the metal conduit or cable armor itself can serve as the EGC, provided that it meets the requirements of the NEC. It's also important to consider the type of equipment being grounded and the environment in which it is located. For example, equipment located in wet or corrosive environments may require special grounding methods to ensure that the grounding system remained effective over time. In summary, sizing grounding conductors requires careful attention to the requirements of the NEC and a thorough understanding of the different types of grounding conductors and their respective roles within the electrical system. By following the guidelines outlined in tables 250.66 and 250.122, and by consulting with a qualified electrician or electrical inspector, it's possible to ensure that the grounding system is safe, effective, and compliant with all applicable codes and regulations. Now, let's delve more deeply into the practical considerations and nuances of selecting and installing grounding conductors, ensuring a comprehensive understanding of this critical aspect of electrical work. When working with grounding conductors, it's essential to consider the material of the conductor, typically copper or aluminum, as this affects its ampacity and suitability for different applications. Copper is the most commonly used material for grounding conductors due to its excellent conductivity, corrosion resistance, and ease of installation. Aluminum conductors are less expensive than copper but have a lower ampacity and are more susceptible to corrosion, requiring special considerations when used in certain environments. When selecting grounding conductors, it's also important to consider the type of insulation or jacket, if any, and its suitability for the intended environment. Grounding conductors are typically bare or insulated with green insulation to clearly identify them as grounding conductors. The insulation must be rated for the voltage and temperature of the circuit and must be resistant to moisture, chemicals, and other environmental factors. In addition to sizing and material considerations, the installation of grounding conductors must comply with specific requirements outlined in the NEC. Grounding conductors must be installed in a neat and workmanlike manner, and they must be securely connected to the equipment and to the grounding system. Grounding conductors must also be protected from physical damage such as abrasion or impact, and they must be supported to prevent strain on the connections. When connecting grounding conductors, it's important to use appropriate connectors and methods to ensure a reliable and low impedance connection. Connectors must be listed for the specific type and size of conductor being used, and they must be installed according to the manufacturer's instructions. Common types of connectors for grounding conductors include compression connectors, set screw connectors, and crimp connectors. In some cases, grounding conductors may be connected using exothermic welding, which creates a permanent and highly conductive bond between the conductors. Exothermic welding is often used for grounding electrode conductors and for connecting grounding conductors in corrosive environments. Another important consideration when installing grounding conductors is the routing of the conductors. Grounding conductors should be routed as directly as possible, avoiding sharp bends and unnecessary splices. The length of the grounding conductor should also be minimized to reduce impedance and voltage drop. In addition to the general requirements for grounding conductors, there are also specific requirements for grounding different types of equipment and systems. For example, grounding requirements for electrical panels, motors, transformers, and electronic equipment may vary depending on the voltage, current, and application. It's important to consult the NEC and the manufacturer's instructions for specific grounding requirements for each type of equipment. In some cases, supplemental grounding electrodes may be required to improve the effectiveness of the grounding system. Supplemental grounding electrodes are additional ground rods, ground plates, or ground rings that are installed to provide a lower impedance path to ground. Supplemental grounding electrodes are often used in areas with high soil resistivity or in locations where the existing grounding electrode system is not adequate. Regular inspection and maintenance of grounding systems is essential to ensure that they remain effective over time. Grounding connections should be inspected periodically for corrosion, damage, and looseness, and they should be tightened or replaced as necessary. Grounding electrodes should also be tested periodically to verify that they are providing a low impedance path to ground. Testing methods include ground resistance testing and impedance testing. In addition to complying with the NEC, it's also important to follow industry best practices for grounding electrical systems. These best practices may include using redundant grounding conductors, providing equipotential bonding, and using surge protective devices to protect against transient voltage surges. By following these best practices, it's possible to create a grounding system that is not only safe and compliant but also highly effective in protecting people and equipment from electrical hazards. In conclusion, selecting and installing grounding conductors requires a thorough understanding of the NEC, the properties of different conductor materials, and the specific requirements for grounding different types of equipment and systems. By following the guidelines outlined in this comprehensive guide, and by consulting with a qualified electrician or electrical inspector, it's possible to ensure that the grounding system is safe, effective, and compliant with all applicable codes and regulations. It is always important to check your local electrical codes to be sure to adhere to the local rules. In summary, to elaborate, the selection of the grounding conductor involves a multifaceted approach incorporating various factors such as the conductor material, ampacity, insulation, installation practices, and routing, all while adhering to the NEC guidelines and industry best practices. This thorough process ensures a safe, compliant, and effective grounding system, safeguarding people and equipment from potential electrical hazards. Remember, electrical work can be dangerous, so always prioritize safety and consult with qualified professionals when necessary.